Hello everyone, welcome to my programming club. Today we will be solving another daily Leetcode problem, and the problem's name is Cherry Pickup Part 2. So the problem statement goes like this. You are given a grid of number of rows are rows and number of columns are columns in that grid, and it represents a field of cherries where each entry in the grid is the value of the number of cherries that cell can contain. Okay, so let's say 5 is in this particular cell, then it is to be considered that there are 5 cherries present in this particular cell in grid. Okay, so you have two robots, both of them initially placed on top left and top right column of the grid. Okay, top left and top right cell. Okay, so it will be the top left cell on which the first robot is, and it is the top right cell. Okay, it means top means 0th row, and left cell will be the first column, and it will be, right cell will be the last column. Okay, so it will robot 1 will be located at 0th row, first column which is 0th column, and since it is a zero based indexing that is considered in this problem, so that's why, so this is the first row and this is the last column. Okay, if we consider a zero based indexing, so these are the initial positions of robot as indicated in this particular picture also. Then what you have to return is you have to return the maximum number of cherries that can be collected using both robots, following provided that following rules are followed. Okay, so what are those rules? From each cell, current cell in which the robot is in, let's say the robot is in this cell, then it can only move to 3 directions. Okay, it will only moving downwards. Okay, starting from the very top row, and the 3 directions are that either it can move to a previous. Okay, you will also always consider one row below for the movement of the robot. Now we may ask that what will be the column number that the robot will be moving to the one row below. So there can be 3 possibilities. One is that it will be moving to one previous column in which it is in, to the bottom row. Okay, so it is, for example, if the robot is here, then one previous column was this, and if you go in one row below, so it will be this cell. Okay, so let me take this image and copy it to a board, then you will be able to understand in a clear way. So if this is the grid given to you, so one previous column was this column, so this is the current position of robot, and one row below will be this position. Similarly, same column and one row below. Okay, this is another option, and let's say the grid is not ending here, instead of that there is another column here. Let's consider this is a imaginary column, so next column will be this column, and one row below will be this cell. So these are the 3 options that robot will be having. It is very well understood that this column will not be there in the grid, so we are not allowed to go outside the boundaries of the grid. Okay, so only these 2 options will be considered. Okay, then the second condition is that when the robot passes through a cell, it picks up all the cherries. Okay, it do not left anything out. Okay, for let's say one robot is entering this particular cell which is having value 5, then this robot will consume all the cherries or pick all the cherries what are present in this particular cell, and it will be nothing left for, let's say the second robot also decide to come here, it will be nothing left for the second robot. Okay, so that's the case. And when both robots stay in the same cell, only one takes the cherries. Okay, it's mentioned that, let's say both of them were able to reach this particular cell which was having 5 value. Okay, this robot will also be able to reach here, and this one will also be able to reach here. Let's say they both decide to go to the same cell, so only one of them will be able to pick all the cherries. Okay, so this particular cell will be considered only once while you are counting the number of cherries that both robots together can pick. Okay, so both robots cannot move outside the grid any moment. So I already mentioned that it cannot be possible that you move outside the boundaries of the grid. Okay, so both robots should reach at the bottom of the grid. It's mentioned that both of them should be reaching at the bottom of the grid. So it should not be the case that, let's say you move only one robot to the bottom of the grid and another one is halfway there. Okay, so let's say you decide to do something like this. Okay, so one of them is reaching, and let's say another one was also going, it reached till here, and you ended searching for the maximum cherries that can be picked. So it should not be the case. Okay, and then both robots should reach at the bottom. Okay, it's mentioned earlier. Now let's move towards the constraints of the problem. So the number of rows and columns will be of order 70, and the values in the grid are of range from 0 to 100. Okay, so for simplicity, what we will be considering is that we will be moving both robots together in to one row below. Okay, why is it so? Because let's say if you decide to separate their movements out, then it will be difficult for you to keep track of if let's say second robot is visiting, then it will be difficult to keep track of what path first robot have already taken and what cherries it have already consumed. Okay, so to avoid that difficulty, what we are doing is we are moving them simultaneously to one row below. Okay, so firstly they will be covering the first row, then they both will come together to the one row below, then they'll come to the next row, then they will come to the next row. So both of them will be moving together. Okay, so first of all we will be considering a brute force way to solve this particular problem, and we'll be seeing that whether that brute force way is sufficient to solve this particular problem or not. Okay, so brute force way. So you know that for each robot 3 possibilities are there of movements. Okay, and if you are moving both of them together, then how many number of combinations are there? 3 into 3. Okay, and these number of combinations will be repeating how many number of times? Okay, 9 combinations will be there, and you will be considering for every row that is there. Okay, these are rows. So rows can be numbered from 0 to row minus 1. Row is number of total rows. Okay, so let's say these are your rows, then each row will be having 3 combinations of these 2 robots. So 3 into 3 combinations, which will be 9. So 9 into 9 into 9. Okay, so how many times this 9 will be repeated? It will be repeated 9 into number of rows. Okay, So for us to consider all the combinations, these much number of operations will be required. Okay, all if you want to consider all the combinations of both of the robots moving simultaneously, then we should be considering these number of operations. So here both robots are moving simultaneously. Okay, and if they move simultaneously, then these number of operations will be required, and number of rows, it is mentioned there that maximum it can be 70. So 9 raised to power 70 it will be, you know, these number of operations will be required about your solution to at least, you know, generate all the combinations that are out there, and we'll be picking the combination which is giving us maximum number of cherries picked. So even if we want to consider only generating all the combinations, then also it's a very huge number of operations, and it is very much greater than the operation limit that is there, which is 10 raised to power 8 operations limit. Okay, these are ops required by our solution to even, you know, let alone picking the maximum solution combination providing maximum cherries. Even to generate all the combinations, this much number of operations will be required, and this is the operation limit. Okay, what happens is that if let's say the number of operations required exceeds or become equal to this operation limit, then you may get a TLE, time limit exceeded, and your solution will not be accepted. So in order to get your solution accepted, you should be, you know, doing some optimizations through this brute force approach. Optimizations are required. Okay, now we'll be seeing that how will we optimizing this particular problem or particular approach, to be precise. So let me take another slide. So till now we know that every row will have a different board state. Okay, so in this particular row, let's say robots will be at some particular cell, and okay, both robots will be at some particular cell. If we take this row, okay, then these both robots can be at some other particular cell. Okay, let's say they are there. So this is how you can say that each row is representing a different combination of columns. Okay, so different combination of column can be represented by each row. Let me write here, each row have different combination of columns that robots will be in. What I mean by this particular thing is, let's say initially it is known to you that initially your robots will be at 0th column and the last column. Okay, calls -1, and this will be your 0th row in which they will be present. Okay, now let's say in another move we definitely for sure know that they'll be moving one row downward. So okay, it will be the next row. Now the question arises, in which columns they will be moving. Okay, so we know that each of them will be having 3 options, okay, to move, and provided that those options are within the boundaries of the you know, grid, they'll be making a move to one row below, and both of them will be doing simultaneously. So let's say some row number 1 is having some column 1 and column 2 combination. So this will be the column location of robot 1, and this will be the column location of robot 2. On which row? First row. Okay, now let's say they move and they move to one row below. It is the second row. Okay, this is the row. Okay, these are row numbers, or if you may want to call them indices, then it's fine also. So row number. So there can be another combination here. So let's say they decided to move. Okay, so this will continue. Now you can see a pattern here, that for each row number there can be a different combination of column 1 and column 2. Okay, so let's say your subproblem, not particularly subproblem, one combination of one such combination can be, let's say there were 3 rows in total. Okay, so one combination can be, for the 0th row you are at A and B. Okay, and then you move to the first row, and then then each of them will be moving. Let's say first robot moved to the C column and this moved to the D column. Okay, so I am not denoting them by numbers right now. I am using alphabets to denote column numbers. This is robot 1 and this is robot 2. Okay, so here also it was robot 1 and it was robot 2. Okay, these are columns and this is row. Let's say then they move to the very last row that is there, and they move to some column, let's say E and G. Okay, now this is one combination that they decided to take. Now let's say there is another combination. Okay, for the 0th row, initially for the 0th row it will be same, or since we have mentioned that they will be having a fixed starting point. Okay, now let's say in the second step also they decided to copy this combination. It will be CD only. Okay, now let's say here in this particular step, or in this particular row, they decided to move somewhat different to this combination 1. So let's say they decided to move in the second row, and they'll be moving in let's call K and L. Okay, so if you see that this particular part both combinations are having in common. Okay, so you can easily see that there is a overlap in these two combinations. Okay, so when you will be encountering this particular subproblem, let me, this color I think should do, or I can change it. Yeah, so when you will be encountering this particular subproblem for the very first time, then it's fine that you are doing some work to calculate it. Okay, let's say you get as a result for this, and then in combination 2 you are again encountering this particular subproblem. Then you again are doing some calculations to calculate what will be the amount of cherries that you can pick. So this will lead you to extra work. Okay, so this overlap will cause you to do extra work, and this is the thing that is causing us to exceed the number of operations, operation limit that is there. So we should somehow store every possible combination that is there for our row number and reuse it whenever we encounter this particular subproblem again. Okay, let's say we stored it somewhere, then instead of doing recalculations here, we will just refer to this result and we will be asking, okay, whether we have this kind of combination. The result will be saying yes, I have. And so you will be not required to do any calculations for this particular subproblem at least. So it will be saving some extra work for you. Okay, so this particular property of a problem in which there are two subproblems which are having some overlap is called overlapping subproblems. Okay, this property is called overlapping subproblems. And for those of you who do not know what a subproblem is, what overlapping subproblem is, I'll be providing a link of an article where you can read about it, what overlapping subproblems are. Okay, and then you will be able to understand it in a much clearer way. Okay, so now let's see the second property which this particular problem will be satisfying. Okay, so second property will be, if you want to know what will be the number of cherries that will be collected by both of the robots when they reach the very last cell, then you should be knowing that what was the number of cherries that were collected before by both of them in total. Okay, so you should be knowing the result of this particular thing to get the result of this particular part. So what you can say by this observation is, solution of bigger subproblems can be derived by combining solution of smaller subproblems. Let's call this solution 1, solution 2, solution 3. So these can be combined and they together can derive the solution of bigger subproblem. Okay, so this particular property is called optimal substructure. Okay, so those of you who are not familiar with this one also, I'll be providing link for this one also. Okay, link of an article describing what optimal substructure is will be provided to you. You can definitely check that out if you are not familiar with this thing. So when these two conditions are satisfied by a problem, then optimization technique can be applied here, which is dynamic programming. Okay, in nutshell, what dynamic programming is, I think it will be good that if you know, I'll be giving you a link also for this one also, and instead of explaining for the to the completeness what dynamic programming is, I'll be asking you to simply head over that link and read about it in case you are not familiar with what dynamic programming is. Basically, you store your results for each intermediate state that will be there, and whenever you say that okay, this state is seen before, then you will be referring to the result instead of doing recalculations. Okay, so this extra work that we were doing here will be easily avoided. Okay, and this is one step of dynamic programming. Another step is that for deriving the solution of a bigger subproblem, okay, we'll be using the solutions of smaller subproblems. Okay, so it's a twofold process. So that's how dynamic programming works in general. Now if it is decided that okay, this problem satisfies the criteria so that dynamic programming can be applied, so next step comes that we should be knowing that how many state variables or how many variables are there that represent, that will help you to determine what state are you in. Okay, so one will be your row number, definitely, since you will be seeing here also that row number was constantly changing, and other than that were your column number for robot 1 and column number for robot 2. Okay, so these three variables were there. Okay, So robot 1 column and robot 2 column. Okay, so these three variables were there which were determining your current state. Okay, so these three variables together will determine your current state. Okay, so we know that three state variables are there. Now when you know that how many state variables are there, then you come to know that what will be the dimensions of dynamic programming structure, this result, how many number of dimensions will be there for this particular structure that will be storing the results of all the states. Okay, so it will be a 3D structure. Okay, so one will be indicating your row number, another will be indicating your column number for robot 1, and another one will be indicating your column number for robot 2. Okay, so it will be a 3D DP. Okay, so let's see how the states changes here. Okay, so let's say you are a particular row, you are at this row, and you are at some column number 1 and column number 2. This is for robot 1 and this is for robot 2. Then the question that you would like to ask yourself is that what can be the previous states that could have made you to land in this particular state. Okay, so it will definitely be one row previous. Okay, that is for sure. Okay, so there can be three options that can lead you to this particular column for robot 1, and there will be again three options that can lead you to this particular column for robot 2. Okay, so all in all you can say that 3 cross 3 9 previous states are possible. Okay, this previous row will always remain fixed, so in total 9 different combinations of column 1 and column 2 can be there. What will be those? It can be column 1 minus 1. Okay, or column 2 can remain as it is, or let's say column 1 can remain as it is and column 2 can change. Okay, similarly you will consider all the three options that are there. Okay, if you consider it this way, so this was one column previous, this was the same column, and this was one column next. Okay, so this is how you will be generating the combinations. So you know that what previous states can be there. Okay, so these are nothing but previous states. So from these previous states it was just a one jump to your current state. Okay, so what you will be doing is to know that how many number of cherries you can pick while your robots are at this particular position. You will be taking the maximum contribution from these previous states, maximum contribution that either of these previous states can one of these previous states can provide you. Okay, let's call this maximum previous state contribution. Okay, and then you will be adding it to, this is your current state. Okay, now it may happen that your robot is not able to reach your current state. Okay, so let's say it was something like this. There is a huge board and your robots are at the very end. Okay, so this robot can move here, here, or here. Okay, and this one can move here, here, or here. But if you see that these columns are not within the reach of any of these two robots, so you should not be considering filling these states. Okay, this should not be considered by you. So in order to avoid that, what we'll be doing is we will be skipping these states. Okay, I'll tell you in the implementation part how I'll be, avoiding these particular states of columns. Okay, so seems like we are having a state transition equation here. Okay, so the state transition equation is, and there is one thing that you need to keep in mind. Let's say this was the case that there was large number of columns such that there was no overlap. Then there can also be a case that there can be a overlap also. So it can be this case. So see here, both of the robots are able to reach this particular column, but you have to only pick cherries present at this particular cell at only once. Okay, you should be avoiding picking it 2 times. Okay, that should be kept in mind. And other than that, your state transition equation will be, let me take another slide. Let's say you are having a cherry picker count, then it will be your row number, then there will be some column on which your robot 1 is present, and there will be some column on which your robot 2 is present. Then it will be value of grid at row and column 1. So number of cherries that are present in this particular column, and number of cherries, this one is for robot 1, that robot 1 will be consuming, and this one will be for robot 2 that I am writing below, column 2. Now this one will be done when when both of the robots are at different columns. So it is the case when column 1 is not equal to column 2. If let's say both of robots are at the same columns, then instead of picking the same cell twice, you should be picking the cell only once. Okay, so it will be grid row, and since column 1 and 2 are equal, so we can take either of them. Okay, this is the case when column 1, let me change the color. This is the case when column 1 is equal to column 2. Okay, so you will be picking this only. Then you will be adding the contribution of max previous state contribution to it. And if let's say this is the case that, okay, I will be explaining this case that how to avoid these columns which are not reachable. Okay, I will be explaining it while I will be explaining you the implementation to you. Okay, so this is how the state transition equation will look like. Okay, and let's see the implementation part. So we'll be initializing the entire structure that we are using to store the intermediate states with -1. Okay, or you can use any value that that is not present in the grid. Okay, instead of -1 you can use, since the values of a grid are only limited to 100, you can use integer dot maximum value here also. Okay, so you can use int max can be used here. Okay, and this particular thing can be initialized to, or not exactly int max, we are required to pick the maximum cherries, so we are taking int minimum. Okay, that can also work. Here also you can change. So what we are doing is, this structure we are using to store the results of intermediate states and build the solution for bigger subproblems with the help of smaller subproblems. This dynamic programming structure we are using to store results for intermediate states and build solutions of bigger states by using solutions of smaller states. Okay, so what we are doing is, initially we are initializing everything which is present in this dynamic programming structure to int minimum. Okay, so this is we are doing to avoid using these columns in our calculations which are not reachable by any of the robot. Okay, so then there will be 3 options for each robot to move 1 row below, 3 options for columns for robots 1 row below the current row. Okay, and then we are populating our dynamic programming structure or dynamic programming data structure that we are using to store the result of the states. Populating our DP structure. Okay, so I'll be explaining this part. Then once you have populated your dynamic programming structure successfully, then you can easily know that you will be having maximum whatever the answer is present for you, you will be having it here only. Okay, so you will see what is the maximum number of cherries that can be there in the last row of this DP structure. So how this thing will be working? First of all, let's say you are at the very first row. Okay, you are at first row, then you are having only, so you can see that for each row, let me explain this part also. For each row there can be calls into calls number of combinations for values of columns on which robot 1 and robot 2 is present. Okay, so if you are at the first row, then you know that you are at this particular cell for robot 1 and this particular cell for robot 2. Okay, if that's not the case, that you are not on the first row, then you will be taking contributions for current state, contributions from previous states to current state. Okay, taking contributions to current state from previous states. So this particular state will be your current state, And if both robots are present in the same column, then you will be consuming the cherries in that particular cell only once, and if that's not the case, you will be consuming the cherries of those two different cells. Okay, then this is the case in when both robots are at same cell. Okay, and here there are a different cell. Okay, so initially your current state will be initialized with these values. Then you will be seeing what is the maximum previous state contribution. Initially you will initialize the maximum previous state contribution to int minimum. Okay, this is to avoid the avoid us using the states which are not reachable by both of the robots. So this will avoid this part, initializing previous states maximum contribution to int minimum. Okay, so then we will be forming all the combinations of previous states that can be there. I talked you about the 9 combinations that can be there. Okay, so combining these 3 into 3 choices, 9 combinations can be generated. Also you should be keeping in mind that the combinations that you are generating should be valid. It means that the both of the robots are within the grid boundaries. Okay, this function ensures both robots are within grid boundaries. Okay, so now once you know that both robots are within grid boundaries, we have to only check for columns only, because we already know that we are well within the bounds of the number of column rows, since we are having a for loop there which is taking care of that. And then you will be picking up the maximum previous state contribution that can be there. If let's say there is no maximum previous states possible at all, let alone the maximum from them, there is no previous states possible to reach the current state, then what you will be doing is, then you will be marking this current state as impossible to reach. If there is no previous state possible which could have you to come on current state, then you will mark current state as impossible to reach. Okay, here also you will be changing it to int minimum. Okay, and if that's not the case, that the current state is reachable by some previous state, then you will be taking the maximum contributions from all the previous states that are possible. Okay, and simply at last you will be returning whatever is the maximum value that is there in the very last row. Okay, and this will represent your maximum cherries that can be collected by both of the robots. Okay, so I'll be explaining once again here, if you want, that each row is having a different combination of columns. Okay, let me take another slide. So let's say there are some R rows, 0 to R. So each of them will individually represent a different combination of column 1 and column 2. Column 1 will be representing the column in which robot 1 is, in this particular row, and column 2 will be present another combination. So in total there will be 9 possibilities for column 1 and 2 for each row. So that's why it's a 3D DP that we are using. Okay, so that is how we'll be solving this particular problem. If you still have any doubts or any queries in general, then you may ask them in the comment section, and you can see that this is getting accepted also. So thank you for watching. Have a great day ahead.